Hello, welcome to the playlist of videos on essential statistics for data science. Data exploration is the fundamental step in any data analysis activity. I am Hemakumar Kasala, and in this video, I'll explain you all that is needed to get a deep insight into the structured data that can either be numeric or categoric. Understanding the data involves arriving at estimates that judge where the data is located or centralized and how varied the data is. While mean, median, and their variance are estimates that help judge the location of the numeric data, mode and expected value provide the similar insight for categoric data. There are a range of estimates available to get insight into the variability in the data, namely the variance, standard deviation and its variance, percentile, IQR, etc. Let's get into the video and understand each one of them and their significance in detail. Raw data. The raw data comes from many different sources and they are different in types: videos, images, text, measurements, triggers, events, etc. Many of them in the raw form could be unstructured. Statistical methods, however, can only be applied to structured data. Hence, the first operations on raw data should include necessary processing and manipulation to arrive at the structured data out of the unstructured ones. Structured data fall into two main categories: numeric and categoric. Numeric as in height in inches, for example 65, 72, 68, etc. and categoric as in various means of transport like bike, public transport, car, by foot, etc. Numeric data can further be categorized as discrete and continuous. While all possible values for a discrete numerical variable is represented by a collection of isolated points on a number line, all possible values for a continuous numerical variable is represented by an interval on the number line. Binary and ordinal are special cases of categoric data. Binary takes only two values like yes or no, true or false, etc. and ordinal or categoric data that are ordered. Categorizing the data based on its type is essential to apply the appropriate statistical and analytical methods and choose the appropriate visualization for the data. Data structures that we often deal with comes in different types: rectangular data, time series data, spatial data, and graph and network data. Rectangular data is a two-dimensional data structure with rows indicating the records, in other words cases or instances, and the columns representing the variables or features. Time series data contains the successive measurements of the same variable. It is the kind of the data subjected to statistical forecasting methods. Spatial data is used in mapping and location analytics, a more complex one than a rectangular frame. Graph and network data represent physical, like in road networks, social, like in Facebook or LinkedIn, and other abstract relationships. The data exploration that we deal with in this session is aimed at the level of individual data variables that constitute the data structures that we just discussed. Let's start with the measures that are available for estimating the numeric data. Following are the two primary estimates for the numeric data. Estimates of location, that is, the value around which the data is centered, and the estimates of variability, that is, the extent of variation within the data. It's important to notice that measures for numeric data are illustrated here using the dot plot of discrete set of values. That doesn't mean that these measures only apply to discrete numeric data. They apply to continuous numeric data as well. The reason is the estimates of location or variability are evaluated often on the sample data and not on the whole population. Since the sample data are discrete values, even if the population is continuous data, these measures and illustration apply to both discrete and continuous numeric data populations. Estimates for location. The basic step in exploring the data is an understanding where the data is concentrated, also referred as the central tendency or the location. The following measures, mean and the median, provide a good insight on the location or the central tendency. Weighted mean and trimmed mean are special cases of mean, and weighted median is a special case of median. These are effective alternative measures to mean and median under specific circumstances. Though mean might appear as the best estimate, it is not always the case. Data analysis involves choosing the right estimate or combination of estimates to arrive at the conclusions. Mean. Mean is the most common estimate for the location. Mean is just the average, which is sum of all the values in the data set divided by the number of values. Mean, also represented by x bar, equals sigma I equals 1 to n of xi divided by n, where n is the size of the data set and xi is the individual data value in the data set. X bar is also called the sample mean because it is often estimated using a sample out of the population. The sample mean x bar is used to estimate the population mean mu. The expectation is that the sample mean x bar is as close as possible to the unknown population mean mu. In other words, x bar closely equals mu. Mean is an effective estimate when the tails of the data distribution are symmetrical. Sample mean x bar represent the population mean mu more reliably when the sample and the population have symmetrical distribution. That is, x bar almost equals mu. Note, more often a random sample resulting out of a population that is symmetrically distributed will also be symmetrical. At times, the sample distribution could contain long and unsymmetrical tails. That can result in the sample mean x bar dragged towards the longer tail far away from the population mean mu, resulting in x bar not representative of mu. Note, a long tail random sample often results out of a population that has asymmetrical long tails, or fewer occasions can also result out of symmetrically distributed population. In either of these cases, sample mean x bar does not represent the population mean mu faithfully. Hence, the mean as an estimate is sensitive to longer and asymmetrical tails and outliers. They skew the sample mean x bar away from the central value of the data set. Hence, the mean is not the best estimate for central tendency or the location under all circumstances. A few alternative estimates fare better as against the mean. Trimmed mean. Trimmed mean, on the other hand, is an effective alternative to counter the drawbacks posed by asymmetrical tails and outliers. In order to evaluate the trimmed mean, the data set and the sample are ordered sequentially according to their values, and a fixed number of data points are dropped from either ends of the above ordered sequence, such that the dot plot of the resulting data fits into a short-tailed but more symmetric distribution. The mean x bar evaluated out of this trimmed sample is then expected to be very close to the realistic population mean mu. The mathematical expression for trimmed mean x bar equals sigma I equals p plus 1 to n minus p of xi divided by n minus 2p, where p is the number of data points dropped from either end of the ordered sample. It's however important to recognize the potential errors that can creep in while trimming the edges. While trimming or dropping the data points from the long tail end is necessary, one also tends to lose valid data points on the other side in the asymmetrical distributions. One should carefully evaluate its impact on estimating the sample mean while choosing trimming means. Median. Median is another estimate for location or the central tendency. Median is that single data value from the sample which is precisely in the middle and divides the sample data into two halves when the data in the sample is numerically ordered. When the total number of data points in a sample is an odd number, the median is that mid-value in the ordered sample. For example, when the total number of data points in a sample is 101, the 51st element qualifies as the median. When the total number of data points in a sample is an even number, the median is the average of two subsequent mid-values in the ordered sample. For example, when the total number of data points in the sample is 100, average of 50th and 51st element qualifies as the median. Median, unlike the mean, does not depend upon the data values in the sample. It's just the mid-value in the ordered sample. Median, unlike the mean, is insensitive to outliers. Median is an useful estimate in cases where the sample data has longer tails and more outliers. For example, in estimating the average income for a region which is characterized by a few belonging to very high income groups. Mean and median together provide a good insight into the sample data distribution. For a symmetrically distributed sample, mean and the median values are expected to be close to each other. For an asymmetrically distributed sample, the difference between the mean and the median can be significantly larger. While the mean is pulled towards the longer tail, the median tends to drift in the opposite direction. For medium and large sample sets, the mean, trimmed mean and median are good enough estimates to understand the population. Mean and the median are two different measures of the data set, where the meaning of the central tendency is not the same. Hence, exploration of sample data involves choosing the right estimate or combination of estimates and acquire necessary insights on the central tendency and the distribution. Estimates for variability. Variability is a measure of dispersion of the data in the sample set, which is the second important estimate of the data in addition to the location or the central tendency. There are quite a few measures to estimate the variability, namely deviation or error, variance or mean squared error, standard deviation, mean absolute deviation, range, percentile or quantile, and inter-quartile range or IQR. Deviations are measures for each of the data point in a sample with respect to the selected location estimate. Deviation equals data value minus location estimate. The location estimate can either be mean or the median. Deviations provide the basis for judging the spread of the data within the set. Mean absolute deviation. One of the useful estimates for variability is calculating the mean absolute deviation. Mean absolute deviation is defined as follows, where n is the size of the data set, xi is each data value, and x bar is the mean. Mean absolute deviation is the average or mean of absolute deviations of each of the data points with respect to the mean. Larger the mean absolute deviation, wider is the data dispersion around the mean. Smaller the mean absolute deviation, narrower is the data dispersion around the mean. Though very intuitive, Mean absolute deviation is not the most sought after estimate for variability when compared to standard deviation or variance. The reason traces to the legacy statistical theory that squaring operations are found more convenient mathematically compared to absolute value evaluations. Variance and standard deviation are the most common estimates for variability. Variance is defined as the average of the squared deviations and is mathematically represented as shown below. Variance is represented by sigma square. Note, denominator uses n-1, which is also called as degrees of freedom instead of n. Standard deviation, which is represented using sigma, is nothing but the square root of variance. The unit for standard deviation is the same as that of the data. Degrees of freedom. Variance uses n-1 in the denominator instead of n. The reason is a sample size of n introduces a bias in the estimates or underestimates the variance, while n-1 in the denominator counters or compensates that bias, in other words, boosts the estimated variance. The compensation using n-1 is significant as the sample size n lowers. The 1 in n-1 represent the number of constraints in the variance evaluation. In this case, the constraint is the single factor, which is the mean x bar. Variance and standard deviation, like in the case of mean, are sensitive to asymmetrically long tails and outliers. Like in the case of mean, trimming the endpoints of the sample data can be useful means to arrive at acceptable variance and standard deviation values. Median absolute deviation is another estimate for variability. Importantly, like the median absolute deviation is insensitive to asymmetrically long tails and outliers. Median absolute deviation by definition equals median value of the absolute differences between xi and m, where xi represent each data value in the sample and m is the median for the sample. Range is yet another estimate for variability. Range by definition equals xn minus x1, where x1 and xn are the first and the last data values in the sample that is ordered ascendingly. Range is a useful variability measure to understand the data dispersion. However, due to its high sensitivity to outliers, range has to be carefully used in the data analysis. Percentile. Percentile assigns ranking to each data value in the sample. Percentile as a measure can be used to understand the dispersion patterns of the data within the sample. Data in the sample is first ordered ascendingly, and the percentile is evaluated for each of the data value xi as follows. Percentile of xi represented by r equals I divided by n multiplied by 100, where n is the sample size. R, the percentile of the ith data value xi, indicates that there are r% of data values that are less than or equal to xi in the ascendingly ordered sample. Accordingly, since the median is the data in the middle, in other words at 50% position, the percentile of the median, R median, equals 50, represented as R50. Similarly, we can locate 25th percentile, R25, also called the lower quartile, and 75th percentile, R75, also called the upper quartile as well. R0 is the percentile of the first data value in the ascendingly ordered sample, and R100 is the percentile of the last data value. Inter-quartile range, IQR, is defined as the difference between the data value at 75th percentile and the data value at 25th percentile. IQR is regarded as a useful estimate for dispersion since it identifies the range within which 50% of the data around the median is located. IQR is immune to outliers. The estimates of location, mean, median, and variability standard deviation, IQR, and the rest that we have discussed so far provide a fairly good insight into where the data is centered and how the data values are dispersed. Additionally, these values provide useful information with regard to where a given data value xi is located relatively within the data dispersion. Estimates of location and variability could help us answer questions like how far is the data value xi located from the mean? In other words, how many standard deviations from the mean? How much of the data values from the sample of population in percentage or below or above xi? What is the concentration of data in percentage between x number of standard deviations in a given data distribution? In order to have some sense of information for the above kind of questions, there are certain empirical rules available that could be put to use. One such useful rule is the Chebychev's rule. Useful especially when the data distribution under analysis is not surely known to be a symmetrical one. Chebychev's rule provides a sense or clue on what percentage of data is at least expected between k standard deviations of the mean. By definition, Chebychev's rule states that the percentage of data values between k standard deviations of the mean is at least 100 multiplied by 1 minus k square percent, where k is any number greater than or equal to 1. Note, k can also be a real number, for example 1.43. Wish to stress the word at least since the Chebychev's rule only predicts the minimum percentage of data within the given span. In reality, the percentage are often more. Accordingly, the following table provides percentage values for some example values of k. K with a non-integer value 2.3 is highlighted just for illustration purpose. Note, the interval that Chebychev's rule specifies is meant to include the mean in the middle, not any arbitrary interval anywhere in the range. Similarly, since this rule applies to non-symmetric distributions as well, one should be careful in using this rule to evaluate percentage of data below a particular value, percentage of data above a particular value, any arbitrary interval inside or outside a span that is not centered at the mean. A rule that is much less conservative than Chebychev's rule is the empirical rule. Empirical rule applies to data that roughly follows a normal distribution. Empirical rule states that approximately 68% of the observations are within one standard deviation of the mean, 95% of the observations are within two standard deviations of the mean, and 99.7% of the observations are within three standard deviations of the mean. Notice the word approximately as against at least used in the case of Chebychev's rule. Estimates of empirical rule as against the Chebychev's rule is higher in each range as shown below. As against the Chebychev's rule, the empirical rule allows estimating the percentage of data below a particular value, percentage of data above a particular value, and any arbitrary interval that is not centered at the mean. Though value in the above cases is restricted to be one among the two standard deviations above the mean, two standard deviations below the mean, and the mean itself. One of the measures that is often useful in data analysis is to judge the relative position of the data value xi given the mean x bar and the standard deviation sigma for a data set. Z-score is a standard measure to locate the relative position of the data value. Z-score is obtained by subtracting the mean from the data value and dividing the resultant by the standard deviation. Distribution of the Z-score for a normally distributed data set shall look like this. Z-score is also called as the standardized score. Z-score plays an important role in statistical analysis and machine learning. We'll look into these details in later sessions. Now let us look into the measures that are available for analyzing the categoric data. While there exist measures to estimate the location, the value around which the data is centered, the concept of variability does not apply to categoric data. The data is as varied as the number of categories. Hence, there is nothing much to explore. There are two measures for the location: mode and the expected value. Mode. Let's represent the number of delays by cause in a given busy airport for an year using a bar chart. Cause of the delay is a categoric variable and it takes the following values, that is, delays due to carrier, ATC, weather, security, and inbound. Mode is defined as the categoric value or values in case of tie that occurs most often in the data set for a categoric variable. Thus, the categorical value inbound in this case happens to be the mode. Mode locates where the data is concentrated in a given categorical data set. Expected value. Let's take the case at a raffle where 500 tickets are sold at the cost of $1 each. The categorical variable in this case is result, where the values are first prize, second prize, or lose the gamble. The respective gain in each of the above result cases are 99, 49, or -$1 respectively. And their respective probabilities are 1 divided by 500, 1 divided by 500, and 498 divided by 500 respectively. What is the expected value of one's gain? Expected value in this case equals sigma I equals 1 to 3 probability of I multiplied by x of I. Substituting the values for probabilities and the gain values, we get the expected value as -$0.70. Since the expected value is negative, one can expect to lose $0.70 for every ticket one buys. By definition, expected value represented by E of x equals sigma I equals 1 to n of pi multiplied by xi, where xi is the discrete value for the ith categoric value and pi is the probability of occurrence of xi and n is the size of the data set. The expected value is nothing but the long-run average outcome of a categoric variable based on its possible outcomes and their respective probabilities. That brings us to the end of the session on data exploration. Please leave your comments or questions if any, and I'll try to revert back with my response as soon as possible. See you with the next video on the playlist of videos on essential statistics for data science. Bye till then.